कैसे हो बच्चों? लेट्स स्टार्ट ये स्टूडेंट्स आज का सेशन। आज हम लोग गैस लॉज पढ़ने वाले हैं। ओके, सो लेट्स स्टार्ट द गैस लॉज। गैस लॉज पढ़ने से पहले फर्स्ट ऑफ ऑल आई विल से वन थिंग, इंट्रोडक्शन देखो। इंट्रोडक्शन के बाद वाला इंटरमॉलिक्यूलर फोर्सेस वाला लेक्चर देखो, उसके बाद गैस लॉज देखना। ओके, अगर वो दो सेशंस नहीं देखे ना, सबसे पहले जाओ वो वाले सेशंस देख के। ओके, सो लेट्स स्टार्ट द सेशन। क्या बताता है गैस लॉ? गैस लॉ कहता क्या है? पर्पस ऑफ एक्सपेरिमेंट, ये करने का मतलब क्या है? सबसे पहले तो मतलब समझना पड़ेगा ना। टू डेमोन्स्ट्रेट द कॉम्प्लेक्सिटी इन्वॉल्व टू मेजरिंग द प्रॉपर्टीज ऑफ गैसेस रिलेटेड टू कॉम्प्लिकेशन इन अ वेइंग ड्यू टू द बायोन्सी ऑफ एयर, प्रॉब्लम इन प्रेशर मेजरमेंट्स ओवर वाटर एंड नॉन आइडियलिटी ऑफ गैस। क्या मीनिंग है इसकी? क्यों पढ़ना पड़ता है गैस लॉ? तो गैस लॉ पढ़ना पड़ता है क्योंकि जब भी आप गैस का वेट फाइंड करने का ट्राई करोगे ना, तो बायोन्सी से उसका वेट आपको कंप्लीट नहीं मिलेगा, उसका प्रेशर भी आपको इनएक्यूरेट मिलेगा, उसमें भी कुछ ना कुछ प्रॉब्लम रहता है। एंड गैसेस जनरली नॉन आइडियल बिहेवियर वाले होते हैं। अब ये आइडियल बिहेवियर वाला गैसेस का मतलब क्या होता है? गैस विच कैन कंप्लीटली फॉलो पीवी इज इक्वल टू एनआरटी या फिर आइडियल गैस इक्वेशन इज कॉल्ड आइडियल गैस। पर जो गैस बच्चों ये इक्वेशन को फॉलो नहीं करता ना, उसको क्या बोला जाता है? नॉन आइडियल गैस। जनरली सारे गैसेस को नॉन आइडियल गैस ही माना जाता है। ओके, अगर कोई बच्चा सुबह बहुत जल्दी उठता है, काम करता है, तो उसे क्या बोलेंगे? उस टाइप के बच्चे को बोलेंगे कि भाई वो आइडियल स्टूडेंट है। पर जनरली आप लोग को आइडियल नहीं हो गया ना। ओके, सो लेट्स स्टार्ट द टॉपिक स्टार्ट करते हैं। फिजिकल कैरेक्टरिस्टिक्स ऑफ गैसेस। हर स्लाइड का स्क्रीनशॉट निकालते रहना, उसको कॉपी में लिखना है। फिजिकल कैरेक्टरिस्टिक नंबर 1, इट्स अ वॉल्यूम। ओके, गैसेस का वॉल्यूम जो होता है बहुत इंपॉर्टेंट चीज है। टिपिकल इसका यूनिट, वॉल्यूम का यूनिट गैसेस के लिए कौन सा लिया जाता है? लीटर। मैंने बहुत ही सोच समझ के आपको ये सारी चीजें यहाँ पे दी है, तो उसे ध्यान से देख लेना, बहुत इंपॉर्टेंट डेटा है। ये सारे डेटा रेडी हो गए तो आप भी मास्टर हो जाओगे। ओके, प्रेशर गैसेस के लिए बहुत इंपॉर्टेंट रहता है। इसका टिपिकल यूनिट गैसेस के लिए एटमॉस्फेयर या फिर एटीएम। 1 atm इज इक्वल टू 1.015 10⁵ न्यूटन पर मीटर स्क्वायर रहता है। ओके, टेम्परेचर गैसेस के लिए बहुत इंपॉर्टेंट चीज है। ओके, उसका यूनिट लिया जाता है टिपिकली केल्विन। ओके, नंबर ऑफ एटम्स और मॉलिक्यूल्स एंड उसका यूनिट है बच्चों मोल। 1 मोल इज इक्वल टू 6.022 10⁻23 एटम्स और मॉलिक्यूल्स। सबसे इंपॉर्टेंट कैरेक्टरिस्टिक्स, अगर कोई आपसे पूछे गैसेस की सबसे इंपॉर्टेंट फिजिकल कैरेक्टरिस्टिक्स कौन सी है, सो पीवीटी एंड मोल्स आर द फिजिकल कैरेक्टरिस्टिक ऑफ गैसेस व्हिच आर वेरी वेरी इंपॉर्टेंट एंड देयर रिस्पेक्टिव यूनिट्स। टेक अ स्क्रीनशॉट, लेट्स मूव टुवर्ड्स द नेक्स्ट स्लाइड। नेक्स्ट स्लाइड प्लीज। ये दिखाई दे रहा है? कॉन्जूरिंग से नहीं लाया मैं ये बच्चों बॉयल्स, मतलब बॉयल है फादर ऑफ मॉडर्न केमिस्ट्री। कोई यहाँ पे मदर फाइंड करने की जरूरत नहीं बच्चों, ये है फादर ऑफ मॉडर्न केमिस्ट्री रॉबर्ट बॉयल, केमिस्ट एंड नेचुरल फिलोसोफर। ओके, आयरलैंड से। अब इन्होंने क्या बताया? अब देखो बहुत स्पेसिफिक पॉइंट पे मैं बात करने जा रहा हूँ, कोई भी फालतू बकवास नहीं करेंगे हम लोग, सीधे पॉइंट पे बात करेंगे। बॉयल का जो रूल है वो क्या बताता है? प्रेशर एंड वॉल्यूम आर इनवर्सली रिलेटेड एट कांस्टेंट टेम्परेचर। शॉर्टली याद रखना, P proportional to 1/V। P proportional to 1/V। क्या याद रखना? प्रेशर एंड वॉल्यूम आर इनवर्सली रिलेटेड एट कांस्टेंट टेम्परेचर। यहाँ पे टेम्परेचर क्या होगा? कांस्टेंट। आपको बेसिकली तीन चीजें लेके चलना है, P, V एंड T लेके चलना है। क्या लेके चलना है आपको बच्चों? यहाँ पे प्रेशर वॉल्यूम टेम्परेचर लेके चलना है। प्रेशर वॉल्यूम टेम्परेचर लेके चलना है। क्या लेके चलना है बच्चों आपको? प्रेशर वॉल्यूम टेम्परेचर। P एंड V का रिलेशन क्या होता है गैसेस के लिए? P proportional to 1/V but at constant temperature। सिंपल चीज। बॉयल पीवी याद रहेगा? क्लियर? बॉयल पीवी। सो P proportional to 1/V। सो टेम्परेचर क्या रहेगा? कांस्टेंट। टेम्परेचर क्या रहेगा? कांस्टेंट। ओके, अब आप चाहो तो यहां से ऐसा भी लिख सकते हो ना कि P is equal to K by V, so PV is equal to K, K is equal to constant। K का होता है constant, तो आ गया PV is equal to K। As one goes up, the other goes down। Okay, अब आप चाहो तो दो रिलेशनशिप इस तरह से P1 is equal to K, P2 V2 इज इक्वल टू K करके आप यहाँ पर रिलेशनशिप ये वाला लिख सकते हो, P1 V1 इज इक्वल टू P2 V2। ओके, ये होता है बॉयल्स लॉ। स्क्रीनशॉट निकालो, स्केच नहीं बनाना, ये लिखना है, टेक अ स्क्रीनशॉट जल्दी से। सो लेट्स मूव टुवर्ड्स द नेक्स्ट स्लाइड। इसे साफ कर रहा हूं बच्चों में। ओके, नेक्स्ट स्लाइड प्लीज। अब बॉयल्स लॉ क्या है? P1 V1 इज इक्वल टू P2 V2। अब देखो यहां पे क्या बताया, दो कंटेनर लिए, अगर आपने प्रेशर इंक्रीज किया तो वॉल्यूम डाउन हो जाएगा, सही है ना। पहले देखो प्रेशर 1 atm था, अब प्रेशर कितना किया? 2 atm। पहले में प्रेशर 1 atm था, अब प्रेशर बढ़ाया तो वॉल्यूम तो कम होगा ना। प्रेशर क्या किया? बढ़ाया, तो वॉल्यूम क्या हो जाएगा? वॉल्यूम कम हो गया। देखो ध्यान से, अब उससे थोड़ा विपरीत सोचो, अगर प्रेशर कम कर दिया तो वॉल्यूम क्या हो जाएगा? बढ़ जाएगा। तो रिलेशनशिप कौन सा आया? रिलेशनशिप यहाँ पे आया P प्रोपोर्शनल टू 1/V। पर टेम्परेचर क्या लिया हमने? टेम्परेचर यहाँ पे हमने कांस्टेंट कंसीडर किया। दिमाग में गया? टेक अ स्क्रीनशॉट जल्दी से। लेट्स मूव टुवर्ड्स द नेक्स्ट स्लाइड। ओके, यहाँ पे एक और एग्जांपल दिया है बच्चों, डिफरेंट प्रेशर के लिए, डिफरेंट वॉल्यूम के लिए। सिर्फ यही चीज ध्यान रखनी है, P1 V1 इज इक्वल टू P2 V2, P1 V1 इज इक्वल टू P2 V2। लेट्स मूव टुवर्ड्स द नेक्स्ट वन। ओके, नेक्स्ट बंदा देखो, बहुत पुराना बंदा, चार्ल्स जैक्स अलेक्जेंडर चार्ल्स, मैथमेटिशियन, फिजिसिस्ट, इन्वेंटर ऑफ बिगॉन्सी, एंड he was a very popular for what? किसके लिए पॉपुलर है? केमिस्ट्री में बच्चों। उन्होंने एक रूल दिया, चार्ल्स जनरली कोई प्रिंस का नाम लग रहा है ना, चार्ल्स जनरली कोई प्रिंस का नाम लग रहा है, तो हम लोग क्या करेंगे? चार्ल्स को पहनाना है VT। क्या पहनाना है बच्चों? वो फिंगरिंग पहनाते हैं ना, वो वाला। चार्ल्स को पहनाना है VT, तो VT पहना दिया। ओके, तो क्या बचा? P। तो P क्या जाएगा? P जाएगा कांस्टेंट। P क्या जाएगा? P जाएगा कांस्टेंट। दिमाग में गया? V proportional to D। Volume of gas varies directly with the absolute temperature. Volume of gas directly proportional to absolute temperature at constant pressure। अगर आप चाहो तो proportionality रिमूव कर दीजिए। So V is equal to आएगा KT। So V by T is equal to आएगा K। अगर आप चाहो तो V1 by T1 is equal to K। V2 by T2 is equal to K। So V1 by T1 is equal to V2 by T2। Okay, so V1 into T2 is equal to V2 into T1। इस तरह से आप लिख सकते हो। ओके, चाहो तो ये वाला लिखो, चाहो तो ये वाला लिखो, दोनों का मीनिंग सेम है। प्रेशर कांस्टेंट, चार्ल्स लग रहा है एक कोई प्रिंस का नाम, अगर प्रिंस का नाम लग रहा है ना तो चार्ल्स को पहना दो, VT फिंगरिंग पहना दो। ओके, P क्या जाएगा? P जाएगा कांस्टेंट। दिमाग में गया बच्चों? सो टेक अ स्क्रीनशॉट निकालो इसका जल्दी से फटाफट से। पहला क्या पढ़ा? पहला पढ़ा P प्रोपोर्शनल टू 1/V। सो PV इज इक्वल टू K। P1 V1 इज इक्वल टू P2 V2। अब क्या आया चार्ल्स में? V proportional to T, so V by T is equal to K, so V1 by T1 is equal to V2 by T2। क्लियर? टेक अ स्क्रीनशॉट जल्दी से, स्क्रीनशॉट निकाल। हो गया बच्चों, चलो नेक्स्ट स्लाइड पे चलते हैं। जितना बनेगा उतना मेन पॉइंट पे फोकस करना है, सिर्फ और सिर्फ मेन चीजें इसके फोकस करते जाओ, कंसेप्ट इजी हो जाएगा। देखो चार्ल्स जी ने क्या बताया, प्रेशर बढ़ाया, ओके प्रेशर बढ़ाया, हीट दिया, अगर हीट दिया तो वॉल्यूम क्या हो जाएगा? प्रेशर कांस्टेंट रखना है बच्चों, देखो प्रेशर कांस्टेंट रखना है। हाँ, यहाँ पे 1 atm, यहाँ पे 1 atm। अब खुद से दिमाग में लगाओ, हीट दिया तो ये वाले जो मॉलिक्यूल है ना, इन लोगों की काइनेटिक एनर्जी बढ़ जाएगी, मतलब ये वॉल्यूम क्या हो जाएगा? बढ़ेगा। वॉल्यूम बढ़ गया, देखो उससे कम कूल कर दो तो मॉलिक्यूल जो घूम रहे थे इर्द गिर्द, वो सारे मॉलिक्यूल की एनर्जी क्या हो जाएगी? कम हो जाएगी। मॉलिक्यूल की एनर्जी कम हो गई, नजदीक आ गए, कम हो गया, गया दिमाग में। टेक अ स्क्रीनशॉट जल्दी से। लेट्स मूव टुवर्ड्स द नेक्स्ट वन। ओके, अभी जो चीजें हमने डिस्कस की बच्चों, वही चीज यहां पे बता रहा है। लेट्स मूव टुवर्ड्स द नेक्स्ट वन। नाउ द नेक्स्ट वन इज एवोगैड्रो। कितना डरावना है इसका फेस, तो देखो बहुत डरावना है, कोई बात नहीं, ठीक। एवोगैड्रो ने क्या बताया बच्चों? एवोगैड्रो ने बताया एट कांस्टेंट टेम्परेचर एंड प्रेशर, द वॉल्यूम ऑफ गैस इज डायरेक्टली रिलेटेड टू द नंबर ऑफ मोल। मतलब कि अगर आपने टेम्परेचर एंड प्रेशर को कांस्टेंट ले लिया, टीपी कांस्टेंट कर दिया, सो V प्रोपोर्शनल टू N होगा, V प्रोपोर्शनल टू N होगा। बहुत 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 इंपॉर्टेंट रिलेशनशिप बच्चों। सो V इज इक्वल टू क्या आएगा, Kn आएगा। सो V बाय V1 बाय N1 इज इक्वल टू K, V2 बाय N2 इज इक्वल टू K। सो V1 बाय N1 इज इक्वल टू V2 बाय N2। लिखोगे ना, ठीक है ना, दिमाग में गया कि नहीं गया? बहुत इंपॉर्टेंट रूल, एवोगैड्रोस रूल। ओके, दिमाग में गया। एवोगैड्रो ने क्या बताया, टीपी को कांस्टेंट कर दो तो V प्रोपोर्शनल टू N जाएगा। अभी हमने क्या पढ़ा, गैस की फिजिकल कैरेक्टरिस्टिक कितनी होती है, बेसिकली 4। कौन सी? प्रेशर, वॉल्यूम, टेम्परेचर, मोल। बॉयल एंड चार्ल्स ने पीवीटी पे बात किया, ओके। एवोगैड्रो ने पीवीटी एंड मोल पे बात किया, ओके। सो लेट्स मूव टू द नेक्स्ट वन। अब एवोगैड्रो का रूल यहां पे आपको बताया गया है, ओके। प्रेशर कांस्टेंट 180 एम, क्या टेम्परेचर भी कांस्टेंट? टेम्परेचर भी कांस्टेंट। अगर गैस ऐड किया तो वॉल्यूम बढ़ेगा, गैस निकाला तो वॉल्यूम कम हो जाएगा, बात कर लिया। गैस ऐड किया तो वॉल्यूम बढ़ेगा, गैस निकाला, गैस ऐड किया मतलब नंबर ऑफ मोल्स ऐड किए। अगर मोल्स ऐड किए तो क्या होगा, वॉल्यूम बढ़ेगा। मोल्स कम किए तो वॉल्यूम कम हो जाएगा, बात क्लियर, ओके। टेक अ स्क्रीनशॉट निकालो इसका, ओके। सो लेट्स मूव द नेक्स्ट वन। लास्ट वाला बंदा आया, देखो चश्मीश बंदा क्या आया, जोसेफ लुइस गैल्यूसेक। ये बहुत ज्यादा एक्सपेरिमेंट करते थे बच्चों, बहुत ज्यादा एक्सपेरिमेंट, गैल्यूसेक बहुत ज्यादा एक्सपेरिमेंट करते थे। देखो सारे बंदे फ्रांस से, कोई बात नहीं, ठीक है, आपका भी नंबर आएगा, पढ़ाई कर लो अच्छा सा। गैल्यूसेक को खेलने का बहुत शौक था। सो P प्रोपोर्शनल टू T एट कांस्टेंट V, P प्रोपोर्शनल टू T एट कांस्टेंट V। बॉयल को बहुत पीने का शौक था, सो P प्रोपोर्शनल टू 1/V एट कांस्टेंट T। चार्ल्स जो था उसको फिंगरिंग पहनने का शौक था, सो V प्रोपोर्शनल टू T एट कांस्टेंट T। ओके, बातें क्लियर हो रही है, दिमाग में जा रही है कि हवा नहीं बनाना। चलो ये क्लियर हो गया। देखो, एट कांस्टेंट वॉल्यूम प्रेशर एंड एब्सोल्यूट टेम्परेचर आर डायरेक्टली रिलेटेड टू ईच अदर, बात क्लियर। अगर चाहो तो P इज इक्वल टू KT लिखो, अगर चाहो तो P1 बाय T1 इज इक्वल टू P2 बाय T2 लिखो, बात वही है। समझ में आ गया? टेक अ स्क्रीनशॉट निकालो इसे। लेट्स मूव टू द नेक्स्ट वन। अब डाल्टन की बारी आ गई। देखो डाल्टन जी ने क्या बताया, डाल्टन बहुत अच्छा है। देखो पोज कैसा दे रहा है, उस टाइम में नहीं था इंस्टाग्राम, बाकी ये फेमस होता बहुत ज्यादा, ठीक है। चलो कोई बात नहीं। देखो डाल्टन ने क्या बताया, डाल्टन ने बताया कि एक कंटेनर लिया, कंटेनर में 3 अलग अलग टाइप की गैसेस ले लो। एक गैसेस का कुछ प्रेशर 180 एम, दूसरे का 280 एम, तीसरे का 380 एम, तो कुल प्रेशर कितना होगा? तो बहुत छोटा बच्चा और उसे भी मालूम पड़ेगा कि 680 एम, वही बता रहा है। देखो, total pressure in container is the sum of the pressure of each gas would exert if the were alone in the container, बात क्लियर। मतलब टोटल प्रेशर कितना बनेगा, सबके इंडिविजुअल प्रेशर जितना, ओके, सबके इंडिविजुअल प्रेशर जितना बनेगा टोटल प्रेशर, ओके। सो आई एम श्योर दिस वन इज क्लियर, समझ में आ गया, डन। टेक अ स्क्रीनशॉट। सो बच्चों आज के लिए बस इतना ही, हमने बेसिकली 4 चीजें यहाँ पे क्लियर कर दी, ओके। सॉरी, बॉयल, चार्ल्स, गैल्यूसेक, डाल्टन एंड एवोगैड्रो। सो 5 रूल, ओके, 5 फंडामेंटल रूल है। फिर से एक बार अगेन वीडियो को देख लो, उसे प्रिपेयर कर दो, ओके। कल फिर मिलेंगे नए सेशन के साथ, नए टॉपिक के साथ। तब तक के लिए इसे कॉपी में लिखो। एंड थैंक यू सो मच फॉर वॉचिंग दिस वीडियो। डोंट फॉरगेट टू लाइक दिस वीडियो, डोंट फॉरगेट टू कमेंट दिस वीडियो, ओके। मेहनत करते रहो, कल फिर मिलेंगे, ओके, बाय बाय।
Robert Boyle was an Irish scientist in the 1600s, and it's actually from his experiments that we get Boyle's law, which actually preceded the ideal gas equation, and we've already shown that. But we're going to work backwards, and we'll use Boyle's law to prove part of the ideal gas equation, and we get a little bit of history along the way, which is always fun. So Boyle was experimenting with gases, and he had a big J tube set up in the entrance of his house, which I'm sure his wife was thrilled about. And so he trapped some gas in that J tube, and he filled the bottom of the tube with a little bit of mercury, which trapped that gas on the closed side because mercury is a pretty dense liquid, and gas has a hard time kind of moving through it. So it trapped a little bit of that gas on the other side. And so this left the open side exposed to the atmosphere here, so that you have the pressure of the gas on one side and the pressure of the atmosphere on the other. And we know that they're pressing down with the same amount of pressure because as he started, the height of the mercury was the same on both sides. Now things got really interesting when he added a bit more mercury because now the two levels didn't equalize. Instead, they were offset. And what this meant was that the trapped gas pressure over here was greater than the atmospheric pressure, such that the gas pressure was equal to the atmospheric pressure plus the fluid pressure of the height difference. And you can think that the gas is pushing down on this part of the mercury with the same force or with the same pressure as the atmosphere pushing down over here, plus this bit of fluid over here pushing down. Now, he added a bit more mercury, which compressed the gas even more, making its volume less, and he found that there was an even greater offset in the two fluid heights. And he correctly took this to mean that the gas was exerting even more pressure because now the gas pressure is equal to the atmospheric pressure plus even more fluid height. And so Robert Boyle plotted this data, and these are the values that he got in the middle of the 17th century. He plotted the volume in cubic inches, and he plotted the pressure in inches of mercury, and he was measuring that height difference for the pressure. And so starting off, his volume was 117.5 cubic inches, and his pressure was 12 inches of mercury. And as he filled the J tube with a little bit more mercury, he had a volume of 87.2 and a pressure of 16 inches of mercury. And as he continued to fill it, he got a volume of 70.7 with a pressure of 20 inches, and continued for a volume of 58.8 and a pressure of 24 inches, and continued and got 44.2 and 32. And as he kept going, he got 35.3 cubic inches and 40 inches of mercury. And then the last value was 29.1 inches of mercury after that's the volume that he had compressed it down to, and 48 inches of mercury for the pressure. And so what he did is he plotted this data, and he graphed pressure as a function of volume. So he had a graph with pressure as a function of volume. And if we look at our pressure, about the highest it gets is 48 inches, so we'll make the top 50, and the middle part we can say is 25 as a kind of benchmark. And if you look at volume, the highest we have is 117, so we'll make it 100, and we'll go a little bit over, and we can kind of fill in our graph. So 50, 25, and 75 cubic inches for volume. And so we see that when our volume is 117.5, our pressure is 12. So that'd be right about here. And we see that as our volume is 87.2, our pressure goes up a little bit to 16. And when we have our volume is 70.7, our pressure is about 20, so that'd be kind of about right there. And when our volume is just about 60, here we have a volume of 20, or I'm sorry, a pressure of 24. And then as our volume goes to 44.2, we have 32-ish, that'd be about right there. And then 35.3 for the volume is about 40 for the pressure. And then right under a pressure of 58, our volume would be about 29, so about right there. And so what we have when we plot pressure as a function of volume is we have a hyperbola. And what we see is that as the volume drops by half from about 50 to 100, the pressure essentially doubles, and as we go from 50 to 25 for the volume, we go from 25 to 50 for the pressure about. So we have an inverse relationship for the pressure and the volume. So if we graph volume, then as a function of the inverse of pressure, we get this graph. We've got volume as a function of the inverse of pressure. So we're going to need the inverse values of all of our pressures. So 1 over 12, the inverse of 12 would be 0.08, and 1 over 16 for the inverse of 16 would be about 0.0625. And if we continue finding the inverse values of these pressures, we would get 0.05 for 20. Then 24 would be 0.042 about, and then 1 over 32 would be 0.03125, and 40 would be 0.025. 1 divided by 40 is 0.025, and then 1 over 48 is 0.0208. And so we can populate our graph with these values, and about the highest inverse pressure value we have is 0.08, and about the lowest is 0.02, so we can kind of fill that in here. And we're still working with the same values for volume, so the highest is a little bit over 100, and then we can put in 50 and 25 and 75. So when our volume is 117.5 cubic inches, the inverse pressure would be about 0.08, and then as we go down, 87.2 would be 0.0625, and 70.7 would be 0.05 right in the middle here, and then 58.8, just about 60, would be 0.042, and 44.2 would be 0.03125, and then 35.3 would be 0.025, and 29.1 would be 0.0208. And this isn't a perfectly clean graph, but we do see that when we graph volume as a function of the inverse of pressure, we get a straight line. And if we write this straight line graph as an equation, it would be y is equal to mx plus b. That's the equation for this graph, where m is our slope and b is our y-intercept. But our y-intercept here is 0, so all we really need is y is equal to mx. Well, in our graph, our y value is our volume, and our x value is the inverse of our pressure. So let's fill that in here. If we call our slope k instead of m, if we just use a different letter, then we'll get v is equal to k times 1 over p. And multiplying both sides by p would give us PV is equal to K. Or in other words, the product of the volume and the pressure for a gas is a constant value, just like we see in the ideal gas equation. So let's test this out by going back to those original values that Robert Boyle plotted. If we measure the product of the pressure and the volume here, we'll see that 117 times 12 is just about 1400, and 87 times 16 is just about 1400. And in fact, all of these volumes multiplied by the pressure, the product is always almost exactly 1400. And so one great application of this concept is that if the number of moles and the temperature of an ideal gas are constant, then the initial product of P and V will equal the final product of P and V. So PF and VF for final. And so let's try to use this in an example. If the pressure of a gas in a 1.25 liter container is initially 0.872 atmospheres, what is the pressure if the volume of the container is increased to 1.5 liters, assuming that the temperature doesn't change? And we know that if this is a closed container, the number of particles isn't going to change, so our moles are also constant. And so let's use this idea that P1V1 is equal to P2V2. And our initial pressure is 0.872 atmospheres, and our initial volume is 1.25 liters. And we're looking for the final pressure when the final volume is 1.5 liters. And so the first thing that we're going to need to do is divide both sides by 1.5 liters to isolate our final pressure. And so on this side, we completely cancel out 1.5 liters, and on this side, we cancel out our units of liters, and we get 0.872 times 1.25 divided by 1.5, and we'll retain our unit of atmosphere here, and that'll give us our final pressure, which happens to be 0.727 atmospheres. And just kind of as a final kind of common sense check, this result follows Boyle's law because we increased the volume from 1.25 to 1.5, and so we decreased the pressure from 0.872 to 0.727. On the experiments that led to the PV part of the ideal gas equation, and now I want to talk about the experiments that led to the V equals T part of the equation. So about 100 years after Robert Boyle, there came a French physicist named Jacques Charlet. And if I didn't look up the pronunciation for this man's name, I probably would have said Jacques Charles, but it's Jacques Charlet. And this French physicist also liked experimenting with gas, and actually turns out he was the first person to fill up a hot air balloon with hydrogen gas and fly solo. But in Jacques' experiments with gas and temperature, he found that if you heat a gas in a closed container, say like a piston, so I've got a piston here, and I'll fill it with gas. It'll be green gas. And this piston will be under constant pressure because as the atmosphere is pushing down on top of the piston, then the pressure of the gas pushing up is going to equal the atmosphere. But under constant pressure with the same amount of particles, as you heat this piston, so let me apply some heat here, and what we'll see is that the volume of the gas will also increase. So if I showed the same piston after the heat was applied, we'd see that the gas was taking up more volume, even though there's the same number of particles here. We still have 6 green particles of gas. So this is what the piston would look like after the heat was applied. And so as you heat a system of gas, the volume will also increase. And in fact, the volume increases directly with the temperature, or the volume increases proportionally to the increase in temperature. And I think I can show this a little bit more clearly if I use a plot of gases increasing with temperature. And so this is what a plot of volume expansion would look like for 4 different gases as we're increasing the temperature. This pink gas would be helium. And so at about 300 degrees Celsius, this helium we can see is taking up a volume of about 5 liters right here. And as we decrease this temperature, the volume is going to decrease proportionally. This straight line is showing this down to at 0 degrees Celsius. We've got just a little over 3 liters that this helium's taking up. And then we've got this green gas, and this might be methane. And we're seeing the same thing. As we increase the temperature, we're increasing proportionally the volume that the methane's taking up. And this blue line might indicate water vapor, water gas, steam. And this yellow line would indicate hydrogen gas. But all of these gases can be plotted in a straight line. So in y-intercept form, that would look like y equals mx plus b. And if we substitute the values that we're using in this graph, our y is our volume, so we would see that y is equal to v, and our x is our temperature. So if we fill that all the way in here, we'd have V is equal to mt plus B. Now, if you're wondering why the slopes are different, it's because the different gas samples in this example would have different number of moles, and you can also see that the lines are coming to a stopping point at different places, and that's because that all of these gases turn into liquid at different temperatures. They all have different boiling points. So with methane, the boiling point would be about negative 100 degrees Celsius, but we could kind of extrapolate this line down, and with water vapor, the boiling point is 100 degrees Celsius, so that's kind of why this straight line stopped. But we can extrapolate this line all the way down as well. And the same thing with hydrogen. And if we extrapolate these values out to find their y-intercepts or their b values, we would see something really interesting, and that's that all of them have a volume of 0 at the exact same temperature, which is negative 273.15 degrees Celsius, which is also 0 Kelvin. And so Charles' law is actually another proof that 0 Kelvin is absolute zero, because we can't have a negative volume for gas. All of these gases have to take up some volume. So the lowest temperature that we could theoretically achieve for any of these gases is negative 273.15 degrees Celsius, or 0 Kelvin. Now, if we take our equation, which is V equals mt, and now we don't need the b because our y-intercept is 0, and if we move some variables around, we'll see that V divided by T is equal to m. Or, in other words, the quotient of our volume divided by our temperature is constant. It's the same volume as long as the sample size is the same, so the same number of moles, and the pressure doesn't change. And this is exactly the concept that we've applied to our ideal gas equation. So let's try to use this concept in a problem. If the volume of a piston filled with gas is 4.31 liters at 25 degrees Celsius, then what is the volume of the gas after it's heated to 50 degrees Celsius, assuming that the system doesn't experience a change in pressure? Well, what we're looking at is a change in volume related to a change in temperature, assuming constant pressure and assuming a closed system with constant moles. So this is a perfect opportunity to apply Charles' law. So we need to start with V1 over T1 is equal to V2 over T2. And again, we're just saying that the initial quotient of the volume and temperature is equal to the final quotient of the volume and temperature, because volume divided by temperature is constant. So our initial volume is 4.31 liters. And our initial temperature is 25 degrees Celsius. But when we're using the ideal gas law, we really need to be operating in Kelvin, because Kelvin allows us to not use negative values for temperature. So let's convert 25 degrees Celsius to Kelvin. And all we would do is take 25 and add 273, which would give us 298 Kelvin. So our initial temperature is 298 Kelvin. And we're looking for the final volume, so V2. And then our final temperature is 50 degrees Celsius, and we need to convert that to Kelvin. So 50 plus 273 is going to give us 323 Kelvin. And so that's the value that we'll input for our final temperature. I noticed that I put T1 here. That's actually T2. Our final temperature is 323 Kelvin. So to continue solving this, we need to multiply both sides by 323 Kelvin to isolate our final volume. So times 323 Kelvin, and that's going to allow us to completely cancel out the value on this side, and we'll cancel out our units of Kelvin on this side. And so what we have is 323 times 4.31 divided by 298, and we're retaining our value, or our unit of liters, and that's going to give us a final volume of 4.67 liters. And so thanks to Jacques Charlet, we know that if we're looking at a closed system under constant pressure, then we can predict the change in volume related to the change in temperature, or vice versa. Okay, so continuing the history of the ideal gas equation here, we get to the 19th century with an Italian chemist named Amedeo Avogadro. And actually his name was Lorenzo Romano Amedeo Carlo Avogadro de Quaregna e de Cerreto, but we're going to call him Amedeo. And Amedeo spent a bit of his time experimenting with tiny particles. And in honor of his experiments, the number of particles in 1 mole of something was named Avogadro's number, which is approximately 6.02 times 10 to the 23. And one thing that Avogadro postulated was that equal volumes of gas at the same temperature and pressure contain equal number of particles, whether those particles are atoms or molecules. So for instance, if you filled up 4 balloons to exactly 1 liter at 25 degrees Celsius with different gases, so let's have a green balloon, and we can say that this green balloon is argon. And we'll have a pink balloon, and I'll try to make it the exact same size as the previous one, and we'll say it's nitrogen. And then we've got a blue balloon that we'll say is hydrogen, and again, I'm off a little bit in the sizes, but we're saying that all of these have exactly 1 liter volume. And then our 4th balloon will be yellow, and we'll say it's filled with methane. And so what Avogadro was saying was that at 1 liter, each one of these 4 balloons would have the same number of particles. So I'm using 5 particles, but the point is that all of these balloons would have the same number of particles. And so at 1 liter, each of these balloons would contain 0.041 moles. So 0.041 moles. And if we use Avogadro's number here, that's the same thing as saying that each of these balloons would be filled with 2.5 times 10 to the 22 particles. And so if you think about it, this is the exact same thought behind our value for the molar volume at STP. We said that for any gas, 1 mole at STP would take up a volume of about 22.4 liters. And the fact that we know that this is true for any gas, not just kind of a particular gas, is credited to the work of Amedeo Avogadro. And Avogadro used this idea and some intuition to develop his law, which is V is equal to a constant A, times the number of moles. Which means that the moles of gas, the number of particles of gas in a system, varies directly with the volume, or the quotient of V and N is equal to a constant. And I'm sure that you've used this same intuition when you've blown up a balloon. As you put in more air particles, as you blow more air into the balloon balloon gets larger. So, for example, if we put in 1 mole of air particles, the balloon would be about 22.4 liters. And as we blew more air into it, say another third of a mole, we would increase the volume to 29.88 liters. So another third of a mole of air gets us up to 29.88 liters. Our volume is getting bigger. And if we were to blow even more air into this system, we would increase the volume even more. So another third of a mole of air would bring our volume up to 37.35 liters. Our volume has expanded proportionally to the amount of air that we've increased in this system. And so Avogadro's law validates the V in part of the ideal gas equation because the volume and the moles are directly proportional to each other. So let's put this principle to work in an example. So when 0.15 moles of helium gas are added to a piston containing 0.82 moles of another gas, by what percent does the total volume increase, assuming isothermal and isobaric conditions? So isothermal is same temperature and isobaric is same pressure. So we have same temperature, same pressure, and we're looking for the percent of volume increase related to the molar increase. And so this is a perfect opportunity to use Avogadro's law. So let's start with V1 divided by N1 is equal to V2 divided by N2. And we know this is true because Avogadro's law says that the quotient of the volume and the number of moles is constant for an ideal gas. So the initial conditions would equal the final conditions. And so we have a ratio set up here, and we can rearrange this ratio to say that V1 over V2 is equal to N1 over N2. And here we've got kind of an interesting part that we can actually start using to solve this problem, because what we see is that the increase in volume is directly proportional to the increase in moles. So for that reason, the percent change in volume looks like the final volume minus the initial volume divided by the initial volume. This is just the formula kind of for percent change, which is pretty intuitive. The final volume minus the initial volume, the change divided by the initial volume is going to give us the percent change. And so we know that this is equal to the percent change in the number of moles. So we can say N2 minus N1 divided by N1. And this really gets us to a point where we can use the values in the formula because it gives us an initial number of particles, an initial moles, and it gives us the change in moles. And so we have the final moles as well. So to find the final moles, because it just says that 0.15 moles are added to 0.82, we'll need to add those together. So 0.82 plus 0.15 plus 0.15 is equal to 0.97. So 0.97 is our final number of moles. That would be our N2. So let's substitute these values in. Our final moles is 0.97 minus our initial moles, which is 0.82, divided by our initial moles. And that's going to give us 0.15 divided by 0.82. Now we're at a point where we can solve this and we can just kind of evaluate this expression, and that would give us the total, or the percent of the total volume increase. But I want to take a second and I want to think about how we could think about this kind of with some common sense and use rounding to give us an approximate answer. So 0.15 divided by 0.82 is between 0.15 divided by 1 and 0.15 divided by 0.75. And 0.15 divided by 1 is 15%. And 0.15 divided by 0.75, it goes into 0.75 5 times. And so that would give us 20%, because 1/5 is 20%. And so if we had to think about this expression in a hurry, say on a test, and we didn't have a calculator, we could use rounding to get us a pretty approximate answer. We know that the answer is between 15 and 20%. And it turns out that the actual answer, if you do use a calculator, is really close to 18.3%. So when 0.15 moles of helium gas are added to a piston containing 0.82 moles of another gas, by what percent does the total volume increase? Well, it's just about exactly 18.3%. And we were able to solve this problem with a little bit of critical thinking based on the principles of Avogadro's law.